to substitute audio that might work. We'll see how it goes. Let's get rid of that. Okay, this is where we left off. We finished that group problem here. And we're just going to continue on with going through the hypothesis testing in the same cases that we did for conference numbers. So we did hypothesis testing on a mean, on the difference between two means. We looked at large samples and small samples. And the next situation that we'll look at again, which is going to be handled exactly like we did in Chapter 5, is what happens when you have two data sets. You have two estimates of the standard deviation or variance of those two data sets, but you have some information that justifies the assumption that the two S's I have in these data sets are really estimates of the same variance, the same standard deviation, same noise. So how do we take those two, group together, and do our hypothesis test? So just like last time, we're going to compute a pooled variance, and here's a pooled standard deviation. And our pooled variance is just a weighted average based on degrees of freedom. I'm going to write this a little bit more generally. So if we have several sets of data, several of these, on and on and on, so it's a new n Sn squared. So as I mentioned before, later on, of course, we'll have more than just two data sets. But right now we have this situation. We have two data sets. We have Sx squared, Sy squared, and degrees of freedom associated with each. So we'll just have that formula. So this bottom, that's the total degrees of freedom, and that's what we're going to use, not our tau, but our t-test. So it's a weighted average using degrees of freedom as the weighting factor. Once we figure that out, then this equation looks slightly different. We used to have an Sx squared there and an Sy squared there. But since they're the same, we can just drop the subscripts and then pull them out of the square root sign there and bring up the front. But no real trickery there. And this, since degrees of freedom equals n minus 1 in each case, that's the same. Two ways of writing the same thing. So then we'll do the same hypothesis test step. So why don't we do this as a group problem? Take a minute and... Pardon? That big nasty formula from before, right? You don't have to use that at all. It's just what are the degrees of freedom from the first set plus the degrees of freedom from the second set. Those are your total degrees of freedom. So just like in the conference simulation. Yes. Has it got something strange yet?
It's backwards. It goes 522 to 618. Then you do back, it's 523. You were back to.
Just yours. I guess I must have had some sort of jam. Anyone else have some weird arrangements? All right. What's this?
Degrees of freedom from each side of just n minus 1.
Yeah, degrees of freedom would be n minus 1 for each data set. First thing to find your null hypothesis and the alternate hypothesis. Again, define the alternate hypothesis first, it's easier. And two ways to do that. If you look at the question here, the question leads us to the alternate hypothesis. Another way to do that is, what do the data seem to indicate? That's another way of formulating the alternative hypothesis. And some key words that we want to look at is do we want to know, is this greater than, less than, or just are these two different? And again, ignore all this business. Just got rid of all that. Yeah, I like the I've got 4 here, 6. But later on, it'll be easier. How we have 4 degrees of freedom in this one right here, there's 60 degrees of freedom in this one.
So if the part of the population varies to like the optimal that we can say
We don't look at these numbers to make that determination. It is something else. It is something about we know how we did those two experiments. That's an idea of what is the error. So it's not at all even. The only thing that provenance is just assuming the the reasons for that are not that turned out numbers. The reasons for that are all this how we perform this. Yeah, so we use alpha is equal to 5%.
Oh, is this?
So, 6 degrees of freedom. The degrees of freedom would be, so the degrees of freedom in this, or we're doing here, the 4 degrees of freedom in there, and 6 degrees of freedom in there. So that is just a total of this. Does everyone see where we get 10 degrees of freedom? Let's question. So when we're assuming equal variances, we're just adding up the degrees of freedom that we have for each of our estimates of the variance. So the next thing, now we need to calculate t. All right, the t from our gains. And then we'll see if it falls out in the rejection region or not. So to do that, we need
Is there a way to do that?
One square. Oh, so first, awesome, just fine, it has to do with formula on the notes. That's fine, I like to do it this way first. And just sort of, later on, we'll use it as rapidly. So as long as it's a pretty minor change. So we have 4 degrees of freedom in that variance, and we have 6 degrees of freedom in that guy right there. And I'm squaring those standard deviations to make them variances, 4.6. So I've got 0.2088. Did you get that for SP? 0.0457? Good. So remember, we have these 2 estimates, and we think they're both reflecting the same underlying variance, and the NY we want to weight a little bit heavier than, the SY a little heavier than the SX because there more data points went into it, more degrees of freedom went into that calculation of the noise. So that's why we do a weighted average. Then once we figure out that, now we can get T. So we have Y bar minus X bar minus the hypothesized difference, which is 0. And we have 0.0457 for SP, 1 over NX, 1 over NY. 2.990. So that ends up being right in here. So we reject H naught, accept H1. And what are we testing? Nickel content of steel. So we'd say they're different. Different concentrations of nickel.
It wouldn't matter if you got a negative 2.9 because
Same thing. Yeah, if you got negative, if you did X bar minus Y bar, you get the same conclusion. That would work just fine. Any questions on that? Okay. All right. So this will come back quite a few times. So we're going to be proving variances a lot in the course. And so keep in mind, we've only done 2 variances, but we can extend this to 4, 5, 6 estimates of the variance and bring them all together into one. And we just weight them by how many degrees of freedom in each of these estimates. All right, no questions? Okay, the last case, if you remember chapter 5, then you're ready for it, is now we have paired data. So this means, remember we called that experimental technique blocking, which means there is some source of error that we can see before we even do the experiment. This is probably going to mess up our results. There's a source of error out there. It's going to inflate our noise, which is going to make our test less sensitive than it could be. So we're going to try to think through it and try to design the experiment in a way that we remove that source of error. And so one way to do that is, where that concept is called blocking. We're blocking out sources of error by designing the experiment in a way to remove them. And one of the ways to do that, a common way, is just to pair up your measurements so that it eliminates that source, that particular source of error. And all this is the same as before. So let's look at this. Take a minute. We'll do this as a group problem. So let's first read through it. And think about why they set up the experiment this way. What was the source of error that they were trying to block out? Think about what they were really trying to measure, and what was the source of error that they're trying to block out by paired measurements. Okay, so some of you guys have started, so what's that source of error? What were they trying to eliminate? What source of noise? What was it that was inflating the noise?
The difference between the trucks.
Yeah, the difference between the trucks. Right, so they see this truck-to-truck variation seems quite large. So for each truck, they tested it at both temperatures. So because of that, we want to look at taking the differences between the paired measurements. So again, if we're going to do a paired measurement type test, we have to make sure which measurements are paired and why. It has to be some real physical thing in the experiment. And in this case, that number and that number were taken from the same truck. So that's pretty natural. Don't just look at these, they showed up on the same row. Right? If they used 10 trucks for 40 degrees and not 10 new trucks for 80 degrees, then there would be no natural pairing. How can this track? So again, please on the exam, take a minute to really think through that because it's an easy mistake to make. It's a pretty major mistake. So know when to do the paired t-test and when to do two independent measurement, difference between two units. Okay, so go ahead and finish off the hypothesis test. Set up your null hypothesis or alternative hypothesis. So that's probably. I looked at a few people. I think we're split about 50-50 how to proceed. So there are two tests that we know what to do. One of them we could calculate x bar here, here, and s here, and here, and compare these two means. But if we do it that way, it's wrong for two reasons. One is this assumes that these measurements are independent than these, and it's not true because they're paired up, right? Also, these include the truck-to-truck variations, right? And we specifically designed the experiment to eliminate it. So we don't want to do that. Instead, we're taking one of these, take 40 minus that, and get 0.0195, and so get 10 differences here, get a D bar, and a standard deviation of those 10 differences. So, kind of remember that from chapter 5. These numbers are paired up, so we want to look at taking these differences. Notice the second one is minus 0.012. You always want to subtract them in the same order. Right? If you're going to go 40 minus 80, do it consistently. If you did 80 minus 40, that's okay too, but do it consistently.
Yeah, that
On the exam, I want you to show me some of these.
After we show you those, do we have to show you how to calculate the bar and SC?
Just show it at the bottom, right? Just,
So if we did
yeah.
have calculated.
Yeah, you don't have to show that calculation.
Is mu not 0?
Yes. Yes. Yeah.
So one of these things, we need to trade out all of these numbers within the time frame of mixing them.
Yes. Yeah. On exam, the way to do that is you have to take these differences yourself, come up with these numbers. Generally, on exam, the numbers are 10. I give you less than that. But yeah, you have to take all these differences on the exam, and then average them and take the standard deviation. Quickly, most of your calculators, once you get the this set of numbers. Right.
Do you have to write those down, the differences?
All right, the question is, do you have to write these differences down? Give me at least some of them, so that I know that you did it. So if you can do this in the calculator quickly, at least give me some of them, because if you get the calculation wrong and I don't find any of these, then it's going to be bad. So it's in your best interest to show that you just got that step right.
If you did write it, you think probably
That's, you get the same number as you did next month.
yeah, we would write it differently than we write it in X bar.
But we have to show you some proof that you did it right. Now, once we have these differences, we are doing a confidence interval on the mean of the average of those 10 numbers. Remember, so you got a two-sided test, and you got those hypotheses. Because we're after something that's just different. How many degrees of freedom do we have? Good, 9. And get a T-star. 2.262. Good. Getting ahead of myself. Yes. Mu zero is the mean of your null hypothesis. Get that? Good. Good. so then we write it in the words of the problem. We'd say temperature impacts emissions, and actually a little bit better better way of doing things in your lab reports would not just say these two things are different, but you'd say, well, the emissions at 40 degrees were more than the emissions at 80 degrees, right? And then at that point, we might be a little bit more precise and say they were 0.03631 plus or minus confidence interval more than they were at 80 degrees. Okay, so again, on an exam, be real careful. Make sure you've got the right test. Make sure you know when to do paired data, when to do difference between two means. Any questions on that part? Okay, that is the 6-level testing. We've been doing it all along. So we'll skip on this example. It's just a pretty basic one. Okay, so now this is probably the most difficult concept that you'll get in the course, at least one of them. So if you're sleepy, I'm going to smack yourself around a little bit today. Very appropriate little bit there. So I'm not exactly sure why this is hard, but this is always hard for people to grasp. So it's not that difficult of a concept. We don't want to kind of psych ourselves out, but you've got to really hang with me from here on out until we cover this power stuff. And I'm going to review what I previewed before. And we said, how did I write this? I called this, I think, the true state of things. And I think I said, I want to get exactly what I did before. Let's see. Where did we start talking about this? There it is. Page 613, I had the true state, H not true, I don't know this. Yeah, I want to present it in the exact same order so that there's no confusion. So let's look at this. We said we're doing a hypothesis testing. And we say, when we do this hypothesis test, we first, again, we're going to take a minute, maybe just write this table down. I don't know where we're at, because I'll be building. True state is either the null hypothesis is true or it's false. So that's what's really happening. And then we have our results of our experiment. In the experiment, the results are either we reject the null hypothesis or we fail to reject it. And we might make the right call, which we have those check marks. The results of our experiment have aligned with what's really happening, or we might make a mistake, which means the results of our experiments don't jive with reality, in which case we have made a mistake. And we have those two types of mistakes or errors. One's called alpha error, one's called beta error. You'll also find this nomenclature. Alpha is called type 1 error, and beta is called type 2 error. I'll generally try to refer to them as alpha and beta error. Got the table down? Okay, so remember, in our null hypothesis, step 2 was assume the null hypothesis is true. Mu equals some value. And then we found the rejection region. and we split alpha up in the tails. And last time we said this error right here, the alpha error is the null hypothesis is true, which means that distribution really and truly is centered about that spot right there. And when we sample our data, we get an X bar that yields a T value either here or here in the rejection region. And that occurs simply by random chance. And when that happens, we're going to reject H naught, even though it really truly is true. It really is there. When I say H naught is true, it means this location is at that, or that distribution is at that spot. That make sense? That's going to be key later. And if alpha is 5%, then 5% of the time, simply by random error, we're going to, when we sample, we're going to get a T value from our data that falls in those tails. And we're going to reject H naught when it's really true. You guys seem to be okay with that last time. Does that make sense again? Okay. So now let's start talking about this one. First, and so alpha we said that was how much evidence we require before we reject the null hypothesis. And when alpha was really, really small, we require more and more and more evidence to reject the null hypothesis. And then we thought, okay, that's a good thing. But then you guys rightly thought, well, that probably means we're taking a hit on beta error when we do this. If we think about a court of law, assuming H naught is true means we assume this guy's innocent. And alpha is how much evidence do you require before you convict him? So as alpha goes from 5% to 1% to 0.1%, that means you're requiring way more and more and more evidence to convict this guy. And so that's fine, but then you realize, well, if you do that, if you set up a system to do that, then there are probably a lot of guilty people that will go free. Right? The more and more evidence you require, you're just going to miss some people. And that's what beta error is. Guilty guys going free. Or in our case, the null hypothesis is false, and we don't reject it. Okay, so key thing I said, kind of belated the point, if the null hypothesis is true, it really is centered about this thing, right? So now, let's start thinking about this. When we talk about beta error, the beta error starts with, well, the null hypothesis is false. So that means this null hypothesis is not here, it's somewhere else, right? So, let's think about this now. The steps in our hypothesis tests are all going to be the same. We do H1, H naught, we do H1. Second step, we assume the null hypothesis is true. So we're going to write that we do this again. And then third, we set up our rejection region. I'm just going to say we're going to do it one-sided for simplicity. We set up our rejection region. There's mu equals mu naught. And now let's start thinking about power. Power or beta. Oh, I'll just call it beta. If the null hypothesis is false, it means it's not there, it's somewhere else. So it could be right. If the null hypothesis isn't true, then that distribution is centered somewhere else. And so keep in mind, we're not going to know that when we do our test, right? So what we want to find out is, well, what are the odds that when this happens, when the null hypothesis is not true, we really hope that we get an answer, a t-value in rejection region, right? Because we should reject it, because it's false. So now, this guy right here, as I've drawn it, that's what we're, in our hypothesis test, we're assuming this is true. So we draw that just like we've done before. But of these two distributions, we go out there and do an experiment. Where do our data come from? The blue distribution or the green dot dash? Where do our data drop off?
Blue one, green experiment.
We've assumed the blue one to be true, but the green dashed one really is. So this is the real one that underlies our experience, right? Does that make sense? So we don't know that, but that's what's really happening. So we're going to get a t-value from that data. If we get it, if it turns out anywhere on that side of the rejection, on that side of the line in the rejection region, then we have not committed a beta error. We rejected the null hypothesis when it should be rejected, right? But anytime this dash distribution yields a result in here, what happens? Remember the blue one, going back to this blue one, this is our hypothesis test. We got a t-value in here. We're not going to reject that, right? We just made a mistake because the real distribution. So this area right here, that's beta. So one thing that beta is a function of is, okay, if this dash distribution, if it's really not even close to me, right? If it's way over here, then it's pretty easy for us to determine, right? Almost all our values are going to be in this rejection. But if it's just slightly over, then a lot of our values are going to be in this beta, right? If this dash distribution is slightly shifted over. So, in calculating the power, one of the things that comes into play is, well, how far apart are the assumed distribution, this one, and the real one, which is that one. Okay. Does that make sense so far? Concept? So that's beta, and then 1 minus beta is power. So we don't even think about the power part because that's just a simple switch at the end. Let's just concentrate on getting this beta error down. So generally when I do these problems, how I'll do that is instead of a dash distribution there, what I'll do is I'll draw it below it. So generally I'll draw this dashed one down here and work the problem that way just to make it a little easier to write things. So I'll work on an example problem now. Okay, that's it. That's the concept. So there's not a whole lot to it. So don't be too doubting if you think you got it, because you might. So let's say we're doing this. On these power calculations, go through all the steps of your hypothesis tests, and then we're going to add an additional step to calculate the power. So HA is the same as H1, just different text sometimes denote differently. So we're testing this hypothesis. Mu is less than 80, mu is greater than 80, H not H1. We're using n is equal to 50. We've got S, which is about equal to sigma is 5. And we'll say, and what we're saying is, okay, what's the power of our test to detect the case when the mean is 80? So first thing is just to plow through all the steps we've already done. H naught, H1, well, that's already done for Step 2, this is critical. We still do step 2. We still assume H naught is true. If you get hung up in any of these problems, make sure you're doing all these steps. So H naught is true means, what is the null hypothesis? It says the mean is there at E. Step 3, alpha defined, it's going to be a Z star in this case. Is it one or two-sided? One-sided. So our Z star won't be 1.96, but the other one? 1.645? Over the weekend, a good thing would be just to memorize this Z thing. It's the way to impress your friends. Okay, so Z star is 1.645, and so that's right here. I can write it up here. So that's the rejection region right there.
How do we get the Z star from here?
Tables. From alpha is 0.05, 5% in the tail, go to the table, and that'll give you the Z star. Yeah.
How do we know it's one-sided?
How do we know it's one-sided? Because our alternate hypothesis is only concerned with UB greater than E. Because U does not equal 80 and be two-sided. So we can only reject the null hypothesis if we get numbers not Good questions. So notice we haven't done anything new yet. So the bulk of these power problems are really the same. And we've got this as our alpha. Alpha error of 5%. Okay. When everyone's ready, then we'll ask that beta question. All right. So now we can get to the second question. What happens? So we're worried. You can think of, we're going to do this test. We're going to do it over and over and over again. And we think, okay, this test works, but somehow if we get this, doesn't say what it is, some batch of stuff, if the mean is 82, let's say that could cause some real bad problems. Right? Let's say that kills me. And so we would want to make sure before we test this stuff and ship it out the door, we'll say, if we do this test where we're sampling 50 of these and have an alpha is 5%, how often are we going to send out like a deadly batch of stuff? Right? So that's what the power question is asking. For some reason, and we don't know why that is in this case, but some reason, mu equals 82 is a number of interest. So now we'll say, now let's go to the beta calculation. We're saying, well, what happens? I'm going to try to draw this somewhat to scale. I got no chance. There. All right. That's bad. That's still bad. If the real distribution is at 82, then we'll say, how often do we make the beta error, or how often do we not make the beta error? So drawing it like this, I think, is really good. And one key thing to do is to just extend your rejection region down here. And now think of, if the mean really is 82, then the data would come from this bottom region, right? And we're going to get some t out of it, and if it falls out of the rejection region, we've made the right call, right? We've rejected this hypothesis, and we've done some right work. But if we get any value in here, then we are going to fail to reject the null hypothesis. So I can see how we would not reject this null hypothesis if we got a t value that's not in the rejection region. Okay, so then the question is, how often do we do that? Well, now you're looking at, well, here's this distribution. I just need that value right there. Right. Is that okay so far? Yeah, Dan.
So this is the case where we failed to reject it, that beta paradigm, and we needed to reject it.
Right.
How do we find beta?
Okay, so now we just need to go to the table. So we got a little bit more work to do. We have to find, well, what's the t-value associated with this part right here? It's t is equal to some x bar, namely the x bar star from above, minus 82 divided by, what's s? 5? 5 over the square root of 50.
Why are we using T and what's my name?
Good question. They should be both these things. Sometimes the projector projects t's like these. I can't help it. We still don't know that x bar star, but we can get it. So z star equals x bar star minus 80 over 5 square root of 50.
Maybe 2, or is that?
These are, so it's the same x bar star at the top and the bottom, right? It's the same line, same location of x bar. And we can use this alpha information to figure out what this is. And then we can carry it down here and get our z distribution. So from here, our x bar star equals, I got 81.16. So that means any x bar that we get that's greater than 81.16, we are going to reject the null hypothesis. Is everyone okay with that? We could have done this all along. We were comparing z with z stars. We could have gotten an x bar star every time. And then the nice thing about extending this line down is it helps reinforce that this is the same. So now we have 81.16 minus 82, 5 over square root of 50, and that gives us some z value, which, do I have it? I think I do. Is it minus 1.19? Check that. Yeah, it looks like close.
And why are we dividing by the square root of 50?
Because this is a mean. Right? We're dealing with x bars here, which are means. So the sigma or the noise of x bar is 5 divided by the square root of 50. The sigma of 5 is just for the individual measurements. Okay, if you have a z of minus 1.19, what is that area from the table? Okay. So beta equals 0.117. 11.7% of the time, if we keep this procedure, we are going to commit a beta error. And 5% of the time, we are going to commit an alpha error. So power is just 0.883, just 1 minus beta. Yeah.
But beta error is dependent on what we measured, our real data. It doesn't matter what our alpha is. Right?
Alpha will impact our beta. So if we reduce alpha, what do we do? What happens to this line if I go from alpha of 5% to 1%? Yeah, it moves this way, right? So that means we're getting more and more error and make this final distribution. What's another thing that I can change practically in my experimental procedure? One is, like we talked about, we could pick alpha, and it's a total trade-off between alpha and beta error if we move that line. What else can we do? That's kind of set by the problem. Well, maybe it's a little early to start talking about that. Why don't we do a group problem? Let's drop down to this group problem and work on parts A through C.
And so the answer was 88.3%.
Yep, 88.3% is the power. So yeah, let's just look at these parts correspond to what we just did. So let's break this group problem up and do it into this thing now and then another section later. So before you even start thinking about the power calculation, go through all these steps in the hypothesis section. And so right here, it's giving you an X bar star. Right there. There's some wording in this problem that's not ideal. So for part A, this is a problem that we could have done before I talked about power law. It's just setting up the hypothesis test. Remember the level, that's just alpha. This is where it's really important to draw your pictures, draw your distributions and your rejection regions. part B, and it was, right, what's the power? If this really is so we got a one-sided test, right? Part A, did you get that? Alpha is 0.0668. That's the level of the test. Now the new stuff in part B is what's the probability that we detect the case that the mean is step 12 is an 11. So what's the power of this experimental procedure to detect Y 11.5? Somehow, this would be, oh, okay. But no, I'll keep on, you didn't see that, it's given in the problem, that's one easy answer. But a more real answer would be, somehow, the guys who make this paint realize that if it dries too quickly, it's gonna gum up, or it's not gonna cut, it's not gonna flow well. So somehow they have figured out that a drying time that's too short of 11.5 causes some problems. So that's why they're asking this question of, hey, if we're going to use this procedure to test our paint, how often are we going to detect this really bad situation? find that second picture. This means I would draw it. It's going to be a lot. Assume 11.5 is 30. I think I got the power to the power is 84.84, and the beta is 0.16. Okay, for part B, we're saying, okay, for the situation where the distribution isn't there, it's really here. Make sure to draw this stuff in. Right? So the distribution is there, and extend this rejection region down to cover both of them. So this value is still, that value is x bar star 11.7, right? So now that is that green shaded region. Is that the power or is that beta? Beta, right? It's not a rejection region, which means we would fail to prove the hypothesis when it really is false. So that's beta. Power is over on the other side. So now we need to get this area here. It's from the bottom distribution. So the z we're looking at would be 11.7 minus 11.5. We're assuming the noise is the same. So 1.0. So that gives a 0.8413 right there. So we get that from the table. Okay. You got to remember what distribution you're dealing with, which is the top and the bottom, and when you get these and table values. If you mix it up, on an exam, I can't tell if you don't understand it or if you just mixed up too much. Does this make a little bit of sense? We're going to hit this a few more times to make sure it's there. And now we're going to talk about why it's such an important concept. Sadly, we have to go.